All right, so hi everyone. My name's Alexander Aghili. I'm a undergrad at UCSC, and this last year I participated in the Citrus Aviation Prize, which was a competition. So I'll go into that a little bit. So basically, the Citrus Aviation Prize was a broad scope project. It was a UC-wide competition on urban air mobility innovations. So the goal of the project was for students to design eVTOL simulation and operation systems with a focus on interconnectivity, safety, and sustainable transport. So obviously, this was like a very broad spectrum of like requirements. So that required like proposal, designing, testing, and then putting it all into like a final presentation. Um, And so we had to basically design um, like procedures and routes and different systems for UAM design. And I'll just briefly say for those that are unfamiliar with urban air mobility, there is a push to try to incorporate new types of um, aviation aircraft that are vertical takeoff and landing that can operate in very dense urban areas. And so that's obviously a big challenge for the aviation community since a lot of the airspace isn't really designed for that. There's like small helicopter traffic, but it isn't nearly on the scale of what they're projecting this is going to, you know, create in terms of traffic density. So there's a big push to sort of redesign a bunch of the airspace systems. This is kind of aligned with that goal. And part of what we did in our project was using Scenic to easily create and test different UAM scenarios that we thought were important, quickly collect and aggregate the data from those simulations, and advise on the UAM challenges and potential federal regulations that we think might help this industry emerge. And so part of that was using Scenic with Microsoft Flight Simulator. For those unfamiliar, Microsoft Flight Simulator is a flight simulator. It's kind of like a game, but we thought it would be useful for the project. So I wanted to give an example of what I kind of did. So on the right, you can see there's a ILS procedure for landing into Oakland, which is sort of a typical way that someone would land at Oakland in a aircraft. One of the proposed routes that we had for our system was following a track north over the San Mateo Bridge, flying over Oakland, and then eastbound over the runways. So this is sort of a typical route in the bay where VFR aircraft will be able to like transit the bay, but it does obviously come with some complications because if an aircraft needs to go around, for example, on approach to runway 30, then that would come directly in conflict with another aircraft that was flying over runway 30, trying to transit north or northeast bound. So this was an example of a situation where we wanted to evaluate, what were the different warning systems that potentially would go off, what are different holding points that we could have. Obviously, if there's lots of traffic, we want to be able to um, get them across as safely as possible, but also as efficiently as possible. Because if you end up being extra conservative, you're not going to be able to get the traffic volume through. It's going to cause delays and a whole bunch of other things. So yeah, so that was kind of the problem that we had as one example of what we were trying to evaluate. And so we wanted to set up a scene really quickly using Scenic. And the amazing thing is, we were able to set up this very complex scenario in a few dozen lines. And that's really the amazing things. We were able to so these waypoints here, VP mid, tie dye, trucking, all of that are specific waypoints on departure procedures and arrival procedures. Um, and so we were able to incorporate these waypoints to quickly identify where the aircraft should go. You could also use lat long, altitude, speeds, doing ranging. So this is just one example where we hard code a bunch of stuff. We don't actually have to um, and a whole bunch of other things. So Yeah, it was really cool. I think I have a video. Yeah, so as you can see, just that line of code or that code that I showed you earlier, you just have to, click run, and it set up this scenario where you can see the eVTOL aircraft is running, it's flying, um, and I'll just skip ahead a little bit. Um, and at the same time, there's the other aircraft here that is also on its track. And yeah, so as you can see, all of that was set up really quickly in Scenic, and we're able to collect a whole bunch of data on the simulation, the warning systems, a bunch of other information that helped us sort of evaluate, okay, where is it safe to hold? When is it within FAA regulations of separation? And at the same time, see, our the possible optimizations and things like that. Similarly, we could do things for departure procedures. We tested a bunch of procedures. So this one was something that Joby has proposed for their eVTOL system. This is an RNAV departure that they've proposed. We wanted to be able to test that and collect a bunch of data about that procedure, and how the automation was flying in and all this kind of stuff. So really easy to set this stuff up, really interesting. So just a couple quick lessons. I already mentioned it's useful for data generation, control evaluation, and scenario creation. We were able to test procedures, routes, warning systems, a whole bunch of stuff that was really helpful in our proposal. We ended up winning one of the prizes as well. And something else I'll say is that the choice of simulator is very important. So for our purposes, the Microsoft Flight Simulator was sufficient. But if we ever wanted to extend beyond what we'd done in our prize to something a little bit more rigorous and detailed, to the point of something that regulators might look at, obviously Microsoft Flight Simulator is not going to be sufficient, just because it's sort of a game. The exact physics aren't necessarily perfect, so that's important, as well as like certain limited controls, hidden interfaces, and documentation that is important. And then it also requires upfront investment to build the simulator interface. So you want to make sure you choose that simulator right, because you're going to spend a lot of time if you're working on building additional simulators. You're going to be doing that a lot. And then just quickly on the future work, I think we're going to move to X-Plane so that we can get greater control of the simulator and simulation environment. And then because of the scope of the project, we had to work on a broad spectrum of things. I think in the future, we're going to want to focus on specific components, like certain onboard automations in UAM environments. So that is all. Thank you very much for your time.
Thanks, Alex. So while, oops. So while, if you want to stop sharing, Alex, and Ali, if you want to start sharing your screen, we might have time for a quick question.
Yeah, sure.
Any questions for Alex? All right, then thanks a lot, Alex, and we'll switch over to Ali.
Yes, hello everybody, and sorry
Go
for the
ahead.
meeting of the timings. I thought it's a start at 30. So I'm Ali Nouri, and I guess you see my screen, yeah? I hope at least. Yeah, okay, great.
We can.
Sorry?
We can see it.
Yeah, great. I'm Ali Nouri, and I'm working for Volvo Cars, and I'm doing research also with Chalmers University of Technology. And we with Zensact, we are working on the DevOps for autonomous vehicles, and we want to make it as fast as possible. And with respect to the Scenic, we just recently, at least I recently, get introduced to Scenic, and mostly what you see in my presentation is about the where we want to use Scenic in future. So we didn't start yet with the Scenic, and I mostly present you some of the research that we've done, and we can use Scenic in that. So basically, our pain point is that in autonomous vehicles, basically there are black swans, and although you have different analysis methods well in advance before you send your car on the road, you can always encounter new scenarios that you couldn't think of, what we name black swans. And then by collecting those black swans, you need to act very fast to them to fix those. If they are on some kind of unknown scenarios, you should basically update your software, or if it's a bug, and then update the software in the car as fast as possible to basically avoid those kind of unknown scenarios to lead some kind of catastrophe or some kind of accident. And then when you have enough confidence, you basically extend your functionality, which again, you might encounter new scenarios because, for instance, it was highway pilot, and then you activate the function in the urban area. So you might have new scenarios in the urban area, and then basically you update your software when it's ready. And we want to make it as fast as possible. So this is basically the pain point. What I'm doing research recently on is to looking at generative AI, and more specifically large language models for automating any part of those tasks that we can do. So if I go, I don't know, yeah, the first two papers that we had on this aspect was on hazard analysis risk assessment. Maybe you are not aware of the method. Basically, it is a brainstorming method. So you think of different malfunctions, different bugs, let's say, but in more function level, and then you put those in different scenarios. And for instance, if we look at the airbag can deploy when there is no accident, or can basically not deploy when we need it, when basically during the accident. But it depends on also the scenario, and scenarios consist of speed, type of road, weather conditions, and all of these factors. And this basically hazard analysis risk assessment is a method that engineers normally use, and they bring the scenario in, and then they understand that what can be the hazardous event, and then they derive requirements for them, and then those requirements, they are broken down to more granular requirements, and then they will be translated to software basically, and be a code in the car. And you can have the paper and read it later. But in short, what we did is basically we break the task of this hazard analysis risk assessment to some subtasks. And what can be relevant to this conference is basically the scenario generation. In this work, we look at natural language as a description of the scenario. The main reason is that actually in the original analysis method, it is in natural language because it's for human. And the second thing is that basically it is natural language is a bit abstract. So it can contain a different alternative of each scenario in that specific, for instance, description of the scenario. So one place that we are thinking right now to use Scenic is basically in this step to generate scenarios, and then later we can also argue about the completeness of the scenarios by, for instance, using Scenic. And then in this analysis, then you take the scenarios, you combine them with the different malfunctions, and you can also have your own catalogs, for instance, and then you come up with the hazardous events. And in this case, the LLMs, they are doing that. And each of these white boxes that you see, it is one LLM. In this case, it's GPT-4 only. And with the prompt, we made it expert in that specific task in the context windows. And then it derived the requirements, and then it performed all the basically analysis. Then in the next job, the next work that we did, so we went more in more granular level, basically software development, because if you look at it, hazard analysis risk assessment is on a function level, so it's a bit technology agnostic. And there you need more basically scenarios and malfunctions as a non-dependent on the software or hardware, or what is the software, what is the hardware. In this case, we went layers down in the abstraction level, and we wanted to generate code automatically. And in both works, we wanted to brute force it and make it autonomous. So basically, no human be involved in those tasks, and we made it basically fully automated. So it's not like a Grammarly language helper, basically. In this case, we in the first work, we examine the performance of LLMs for code generation, and then the generated code sent to our simulation environment. The simulation environment can be also, for instance, used. Carla, for instance, can be used, but in this case, it's a minimal simulation environment that we have, which is designed for function level, named SMINI. And then in this specific case, it generates a code for being placed as a decision and control of the vehicle. So the perception is in the simulation and actuation. And this is representing a software architecture in the car. So if you, for instance, want to have a system that automatically generate a code for you, you want to be basically autonomous. And then you should not go and fix the interfaces between different softwares that they are generated. It should basically obey the rules of the inputs and outputs, and does not basically hallucinate on the existing classes or existing inputs or needed outputs. So basically the LLM generate the code, and our pipeline extracted automatically from the answer and sent it to our simulation environment. And then this task goes on, and it generate multiple one, basically what we name generate fast, eliminate fast. So it generate, for instance, 20 instances of the same task description, and then we select the best. And then we have in our simulation environment, we had different scenario descriptions. In this case, it's open scenario, but we again for Scenic, we are looking at from the previous work, hazard analysis risk assessment work, how we can use those scenarios that is generated there, for instance, in Scenic, in this simulation environment. And then it goes
Hey,
on and on. Sorry.
Sorry to interrupt, Ali, but if you could wrap up, we're a little over time.
Oh, sure. Actually, yeah, just I wanted to give the last idea, and then it's at the end. Basically, in that work that I explained is one way. The LLM doesn't get any feedback from the simulation, but then in our next work, which you can go and read basically the detail of that, there is a conversation between the LLM and simulation environment, which here, if we have the scenario basically description or scenario generation as well, for any new function, we can have basically the scenario explanation and have it in the simulation. And then this conversation helps to improve the code as well. So I will wrap up and here. And if you have any question, I can answer and go to more details. Thanks.
Thanks, Ali. And if Luis, you can start sharing your screen. And yeah, any questions?
It's the feedback from simulation getting back to that a lot. So the question is, how exactly is the feedback between the simulator and the LLM?
That's a great question. Actually, the simulation gives you the log, the numerical logs, basically. And then we have different rules, safety rules that they are fixed. That, for instance, if the distance between two cars are nearer than this, then this means collision, for instance. And then there are fixed basically reports that our Python code basically get those numbers, and it says that, oh yes, there is a collision, and this, for instance, at this time it is violated basically, and then this report will be injected automatically to our prompt and sent it to the LLM. Right now, I feel that it can be improved far more. For instance, you can give more details, but at this time, we just wanted to test the idea. So I can say it was effective because in one time it gave the working code at the first step, but there was another case that this feedback loop was also effective. So it's not completely useless, but it can be also improved to give a, for instance, better report. For instance, we can use also LLM to translate those numerical logs in a better way for another LLM. But yeah, this is under investigation right now.
Great. Thanks, Ali.
Thank
Okay.
you.
Go over to Luis next. If you want to unmute yourself there, Luis.
Okay.
Go ahead.
Okay. Hello. Now, yeah, now, thank you. Okay. Hello. My name is Luis, and I'm going to present our work in our lab that we have been doing with my advisor, Professor Alvaro Cardenas, and my lab mate, Diego Ortiz. And this is an application, or I'm going to show you how we have been using Scenic and Verify to study the security of autonomous vehicles. So, oops. As you know, like there are these autonomous vehicles, like there are a lot of companies like Zoox and Waymo that are deploying these vehicles in the reality now. And of course, we expect these vehicles to be deployed like in the next years, like it's going to be like a huge market share. But we have seen that even when there is no attacker, these vehicles not always work as we expect them to work. So we have seen that even without an attacker, there are accidents that these vehicles are involved in. So, for example, with pedestrians and that. But now we have seen another way of attacking these autonomous vehicles. For example, in 2023, there was this example where people put cones in front of a vehicle, and that made the car stop and get stuck in the road. So what we want to do is to study the security of these autonomous vehicles. How can we create, for example, attacks against these autonomous vehicles? And in particular, we are going to use, or we have been using Scenic and Verify. So I'm going to present you one use case that we have been studying. So imagine that we have this string of vehicles and that they are following each other. And now consider that this first vehicle is the attacker. So this attacker can control the acceleration, and the idea is that by controlling this, the acceleration action, the attacker wants that eventually this car crashes, or one of the vehicles behind the attacker crash. However, and so we have this first objective, which is, of course, the attacker wants other vehicles to crash. But if the maneuvers are not properly done, then we may have this other scenario where this vehicle crashes with the attacker, which is something that the attacker doesn't want. So we have these two objectives. On the one hand, we want the attacker to create crashes between the victims, let's say, and we want the attacker to avoid being crashed. So I'm going to show you how we have been using Scenic and Verify for this. So in particular, what we want to find is what is the behavior that the attacker should have to satisfy these two objectives. And in particular, we want to find the set of actions like throttle and brake, such that the attacker maintains a safe distance to other vehicles and the victim's vehicle crash so that the distance is below a safe distance. So this has several challenges. First, the space that we have to search on is like huge because we have like acceleration and braking at each time step. And also the relation between the action of the attacker and the safety and the specifications that we have is not clear. Like we don't know how to quantify easily the relation between a change in the action and a change in the specification that we have. So for that, we have been using Scenic and Verify. And the idea of this is that we constrain the maneuvers of the attacker. So instead of saying, okay, at each time step, we find the control action that the attacker should add, we constrain how the attackers can behave. So for example, if the attacker can only accelerate and deaccelerate, and what are these actions or the maximum accelerations that the attacker can do. And so we define Scenic programs to model the attacker behavior. So I'm gonna show you here an example of this. So here, this is the attacker, and we see that due to this maneuver, these two cars crash. And then this is another attack where the three car crash. So yeah, if you want to see the details of how we did this is the paper that we wrote. We have this paper, and we have this is like an improved version of our initial paper. But here, let's say that we used like several constraints to the attacker. Now we want to have less constraints, and we want to improve our work. So, for example, how can we optimize these two objective functions that are not necessarily aligned? Yeah.
Thank you, Luis. So, Sridhar, if you want to share your screen and while we're setting up, any questions for Luis?
Yeah.
So, does the adversary model assumptions about the adversary, is that also in the Scenic program? Or is it specified as a
Like
what the adversary can do as
what the attacker can do? Yeah, we specified in Scenic as well. Yeah, exactly. So for example, we say that the attacker can only follow like a square signal, like accelerate and then deaccelerate. So we find the frequency that the attacker does that. We find the action that the attacker actually applies, like the maximum and minimum acceleration, and we encode that in Scenic program. Yes.
Thanks, Luis.
Yeah. Okay, so I'm here to describe one of our recent works. So you've all had like hands-on experience with Scenic yesterday, and you've all seen how it's slightly tricky to write some of these specifications and distributions, especially. So what we thought of doing was to think of some sort of a translation where instead of writing this code explicitly, you provide some sort of a video, and we automatically convert it into a Scenic program. So here I have like a real view, and then I superimpose with the corresponding program or simulation that I generate from using Scenic in the simulation engine of your choice, like Carla or MetaDrive. And we want to essentially, the reason for doing this is instead of just thinking of scenarios by ourselves, we want this as to act as some sort of a beginner code to actually think of a repository of scenarios, which can be captured by a dash cam video per se, and extend them in Scenic, import them in Scenic, and then modify them if required, right? Again, adding some sort of Scenic is a data augmentation platform. So if you have some sort of a generate distribution that you have specified within Scenic, you can generate several scenarios which satisfy the distribution and some of the additional constraints that you have specified. There have been pure machine learning directed techniques for some of these data augmentation. Again, this goes back to 2018 as well. I've cited some of the more recent works where they try to understand the positions of cars and build some sort of a scene graph or some sort of a implicit actor and background representation, Gaussian splatter. Again, this is almost like a cottage industry where I give you a video, and in return, you give me another video, which is a modification of the given video, right? So there are many of these that are already there. And compared to that, Scenic is very programmatic in nature. So you are somewhat grounded. You specify the high-level constructs very clearly. Again, it's explainable. You can edit it. In the case of, say, some neural network-based data augmentation mechanisms, you will know that you will get a different video, but the amount of control you have over the video generation isn't too precise. So we want to kind of bring both of them together, add the grounding that you get from the Scenic, add the precise semantics that you get from the Scenic, but also kind of get the diverse scenarios that are out there instead of just whatever we program, right? So we call this Neuro-Symbolic data augmentation. And again, I'll basically give the high-level problem statement, and I'll give the high-level idea. So the input, again, what we want to do is the following. We want to convert a particular video to a Scenic program. So you are given a collection of frames, a sequence of frames. And what we want is a Scenic program. In here, to some extent, because we are only given one scenario, we are not specifically asking for some sort of a distribution in the Scenic program. Like, for example, if you have range and all these constructs, we won't be having those, but given a video, we want to have like an environment, which is the background environment, and the set of collection of agents and actions that are described in the Scenic program, such that when you run the Scenic program in the simulator of your choice, you get something that is similar to the actual input, right? So the correctness part is actually not that easy to measure. So for example, if I actually have like a dash cam video, and say I've generated a Scenic program, and now I've generated a video from the Scenic program, what does it mean for these two videos to be same? I don't have the actual measurements of the dash cam and how far are the cars and all that. So it's in some sense like this warm, fuzzy vibe feeling that we need to say that, oh, these look close enough, so I'll consider that to be correct. But the advantage is that we can do the same, we can apply the same thing for videos that are simulated. So I can take a Scenic program, run it, and get the video, and use this to generate the video, translate into Scenic program and generate the video again. Now I have some basis for saying whether the translation is correct or not. So again, correctness is something that is slightly tricky if you have real world videos, but if you have a video of a simulation itself, this becomes much more easier to define. Well, I mean, we are in the era of foundation models now. So again, we have seen 2-3 examples of this already being used. So our first attempt in doing this was actually to do very straightforward fine tuning. So I'll take a bunch of Scenic videos, and I have a bunch of Scenic programs, which actually, so we generate the videos from, actually we write a bunch of Scenic programs and the corresponding videos. And in our first attempt, we tried to reverse it. That is, can you fine tune just a GPT model where you can take the video and generate the Scenic program automatically. It didn't work to our satisfaction, but then we had like some sort of a two-step framework where we did object tracking, where we took the video, performed the object tracking, used some sort of a GPT-like engine to generate natural language description of the scenario, and then converted the natural language description to Scenic code. And this apparently, I mean, this worked better. Again, here are some of the examples of the real world videos and the corresponding Scenic videos. As I said, again, there is no exact notion of correctness. So we are going here by the vibe. If they look fine, then they are okay, right? But again, we can evaluate some sort of correctness by doing the reverse purely on simulated videos and generate the code and check the correctness. One of the advantages that we wanted to do is to do some sort of environment modification. That is, we can make all the gloomy weather outside to be very nice, or the nice weather to be gloomy. Again, this is one of the applications that we are trying to drive, which is data augmentation, fundamentally using grounding, which you get for free using Scenic. Again, I want to say that this problem is not completely solved. Right now, we can only generate videos that are 5 seconds long. Ideally, we want to be at a place where we can generate a video of 30 seconds long. We are currently working on that. The notion of correctness is also not fully clear to us. So that's another thing that we want to explore as well. So with that, thank you for the attention.
Well, next up is Aoki-san, if you want to start getting them set up while we're with the questions.
Question on the second bullet, when you say physical environment is not completely captured in Scenic, what do you mean by that?
So what I mean is that, say, Scenic only describes the behaviors of the agents, right? For example, I cannot, at least say the environment specification, if you give me a video, I cannot extract, oh, this building is this tall. I might have to add a lot of...
It doesn't specify all the attributes
of the environment. Exactly. So again, maybe there's a way to do it. Yeah.
It's a similar problem to the something
map problem.
Well, there's a map problem, but also, I mean, there's always, it's never going to be a complete match, right?
Yeah.
So in Eddie Kim's work, which maybe we talk about this afternoon on querying videos with Scenic programs, you're looking for a partial match.
Yeah.
Because obviously, you know,
Yeah.
both the Scenic program has stuff which may not be in the video has stuff that may not be here.
Yes.
But you want the relevant things.
Yeah.
So, go ahead.
Okay, thank you for giving us the opportunity to introduce our project and share how we expect to use the Scenic in our project. So we are working on the practical application of the formal method to the real system, in particular automotive systems. So far we are working on practical application of the formula method to the low level of the automotive system, including operating systems. Actually, we successfully verified the commercial operating system for the engine control systems. And that operating system used in Toyota's car, actually, even in my car. And also, they successfully released the commercial tool for the MATLAB Simulink. With the tool vendor named the Gaia technology. So that tool is now on sale, actually. And some Japanese automotive company uses our tool to verify the MATLAB Simulink model for the control system. But now we are going into the autonomous driving systems. It's implemented on top of the such low level the automotive system. So we decided to extend our focus to that part, autonomous driving systems. And we successfully got the project from the government. So this is called the JAIST CREST project. This is one of the biggest research projects in Japan. And it started in October 2023, and it lasting the 5.5 years. And the budget is something like the 1 to the 3 to 3.3 million US dollar, because now Japanese yen is very weak. So in terms of US dollar, it becomes something like this. And our team consists of there 4 PIs. I'm a PI of this project, and the 2 PIs from my colleagues from the JAIST, and the 1 from the Saitama University. We stick in applying formal method to the real system. So we focus on now the AutoWare, which is open source software for the autonomous driving systems. And the open software is managed by the TFO, which is a startup company in Japan. And actually, the TFO team is joined the project under the co-PI, the Takuya, the Saitama University. And our focus is covers from the perception to the control. The idea is the very classical design by contract. So we invent an appropriate contract for the perception, planning, and control module. Then they verify each module against the contracts, that is specification. So this is our approach. And our group, my group, the focus is on the from the perception, planning, perception and planning. No, this one, right? Then okay. So this is an overview of the current our tool chain. So we focus on the AutoWare, and we use the simulator named OSIM. So this is for the AutoWare. Of course, there is a simulator color and connect to the AutoWare, but it's not so reliable, actually, buggy. So actually, the OSIM lab is developed the TFO as well. So it is best fit to the AutoWare, to analyze the AutoWare. And so I think that the Scenic focuses on the end-to-end. So, but we focus on not only the end-to-end, but also the internal data. So we implement the monitor the data inside of the AutoWare. And in order to realize a specific scenario, actually we are following some industry standards proposed by the Japanese Automotive Manufacturing Association. So this is for the scenario-based safety analysis. Also, there is an international standard like this on the UN regulation 157. Yeah. So we are using such kind of the framework. And in order to realize specific scenario on top for the in the simulation, we extended this simulator and also the proposed script language, and so that we follow these scenarios. Now the one idea to use the Scenic is here. So we generate the scenario for the simulator from the Scenic. Actually, he is working on that. He already implemented part of this mechanism. After obtain this data, so we visualize data, and also we are proposing a special language for the perception module. Also, we are proposing the discrete modern language for the discrete scenario. So now we are proposing abstract interpretation of the trajectory to such kind of the discrete scenario. Then we analyze the model checker and the SMT solver, theorem prover, and so on. And this is my part. So we are proposing scenario model language. This is a very discrete behavior. So the one idea to utilize the Scenic is here to analyze this model. Actually, this is very absolute one. So we want to find a concrete scenario from this model using the Scenic. This is one idea. Actually, we enumerate this scenario using SMT solver, but it is very costly, and the number of the scenario becomes a bit large. The computer complexity is actually factorial with respect to the number of the steps. So it is very complex. So I think that the Scenic uses randomization, right? It is efficient. I think that we can efficiently find such interesting scenario from this model. This is one idea. Another idea is explained by Gazon.
So yes, so as a first step, so we use something another
I propose the scenario description language is called the OSIM script. So this kind of language is very simple notation. So that for different scenario, even it's just different a bit about variation, parameter configuration. We need to write another kind of script. So another idea is that we would like to integrate with the Scenic language because Scenic itself we know that it has ability for describe about the randomness parameter, and then so in that sense, so we can write just a single scenario and then so run it, and then so by using some kind of requirement, so we can describe our scenario of interest. So that's the idea. And then so as the first step, so we already successfully make a new simulator, a new interface to our simulator. It's called the OSIM lab, as Aoki mentioned before here. And so in this kind of toolchain architecture, so how to run the OSIM lab, so it's based on the robot operating system, ROS2. And then so we would like to also to implement a kind of runtime monitor, but it's not the end-to-end monitor only, but we also would like to check the internal status of the autonomous driving system. For example, the planning module, control module, or the perception module. Another thing that do not show in this slide is about the safety standards. So for the X scenario, so we consider here, so we should play on the kind of safety standard because we are much concerned about the realism of the scenario. There are a bunch of the research for finding the collision scenario such that collision happen, but we're concerned about what's the realism of the such scenario. In some scenarios, also collision should be kind of unpreventable. But if we rely on some safety standard, then we can separate this scenario is preventable. Another one is unpreventable. So that's, I think, our idea.
Yeah. And then the final one is, yeah. So if you interested in the project, please visit this URL. And also then we have open positions, few. Like one assistant professor for my lab and two post positions for the project. If you are interested in or your colleagues or your friends are interested in please check the code for the position and yeah, these ones. And also upcoming events. So the FM formal method is the biggest conference in the formal method area will be held in Tokyo. And we have a doctoral symposium, and the deadline is mid-January. So if you're interested in, please tell me. And also the Korea, so ICSD held next year. Okay, thank you very much.
And a question on the previous slide, the runtime monitor one, is that something that you are coding by hand?
Yeah, so as the first step, so we already make a very simple one so that it is simply just a train recording. And then so at this moment, we would like to do something like recording, monitoring the safety of the each module level. For example, the control module, the first one is the perception module, and then the planning module, and then control module. And if possible, we would like to do something like repair the output if it violates the safety. Yes.
You don't have a system level monitor?
System level, maybe it can be considered as the output of the control.
Okay.
I think so.
Yeah. The reason I asked about this is that there is some work by a collaborator of ours on translating Scenic to run, going from Scenic to runtime monitors, basically doing ODD monitoring. So this might be useful. So if you have a representation for runtime monitor, they could try to generate the ODD monitor in that representation.
I see.
Is it for the freak data or internal data of the system?
So the whole system. You can
For a whole system.
Also, but it is also for, it's right now it is more towards the on sensors.
Sensor or output the perception module or okay, I see, great.
Okay, I'm curious about it, so let's talk about it. It's a copy, correct?
Other questions? Anirban?
Otherwise, Anirban is, yeah, Anirban first starts setting.
Okay. Thank you.
So to stay on time, we're going to move some of the talks to the afternoon to relevant sessions. Yeah.
So we should finish by. Hi, I'm Anirban Roy. I'm from SRI. My interests are currently neuro-symbolic approaches. So as you know that neural approaches have some limitations. So how to augment that and make it more efficient in terms of data, compute, and running on small devices. I'm also interested in large multi-language model, for vision language model, large language model. And given these models, we are interested in uncertainty quantification assurance. In many cases, for example, medical applications, we cannot be unsure when you are making a prediction. We are recently looking at interpretability, like the newer version of that mechanistic interpretability. So when these models are doing something, why it is doing, what it is doing. And of course, we are a lab with multiple applications, AI for complex situation understanding, cyber-physical design, architecture design, education, and some kind of medical applications. Okay. So currently we are working on this DARPA assured Neuro-Symbolic reasoning program, and where the goal is given a complex kind of scenario where think about the drone flying around a city, looking at multiple cars where there is complex behavior between the cars. So one car is following other car, and there can be multiple convoy of the cars. So how you detect such things? So for example, there's a car going forward, following a car for half an hour and took a left turn and come back to another spot. And it's more like an active perception kind of framework where you're not given an offline video where you have to take this pattern. You have to follow the car and search those activities. Where is the red car following a blue car? The drone has to move around and find these scenarios. To address this problem, we are looking at multiple frameworks. So one thing that we have recently developed, it will be published in ICCV 2025 this year. So temporally grounded video question answering. So LLMs are really good at giving you answers. You give a video, it will give you an answer. They're really impressive, but they're not good at doing this temporal localization. So where somebody's playing, for example, let's say we ask this, what does the boy in red do in the beginning? So we are talking about the beginning of the video, and not only he has to give me an answer, it also has to localize that it's happening from 0 to 4 seconds. And then, for example, what does the lady do in the end of the video? So we need to understand these activities and also localize them temporally so that, and those localization can be thought of as evidences so that we can verify the model based on the answers. I mean, beyond temporal, we can also do it for images, spatial reasoning. And here the goal is again the same. We need to do the reasoning along with the evidence. So for example, if you ask this really large model, like we tried with GPT-4o, you can try with the newer model, GPT-5, and so they're really good at giving you an answer. So for example, look at the evidence from that image. The game is playing in Philadelphia. Or you can ask like, where is the game is playing? It will give you an answer, but it will not be able to localize. And then you can see it tries to localize the ground, but then ground doesn't give you enough evidence so that you can conclude that the game is happening in Philadelphia. But our model, which is trained only with 8 billion parameter, and you can see it tries to localize. I'm not claiming it is accurate, but it tries to at least localize in the jersey. So the jersey number and color of the jersey will give you an idea of which team is playing. And maybe from that, you can get an idea where the game is being played. So these are the things we are trying to do because it is assured. So we want to get some evidences which can be used as an assurance claim later. And in this project, how Scenic can be useful. So we are trying to generate these complex events, but as you can see, these are hard to generate. So if somebody has to drive around and make this thing, it's pretty hard. Flying a drone and where 3 people are driving around, that is hard. So how to develop this kind of complex scenarios using Scenic? And we tried using AirSim, and we had a team working on this thing for 1 year. They are not very successful, you know that, because the scenarios they're coming up with, they are not good enough. So I think Scenic can be really useful in these kind of scenarios where you can programmatically generate scenarios and make variations. And again, we are interested not in just offline activity recognition, not like vision problem, but we are interested in active perception. So find the red car where things are doing. So there is a planning component. You see something, based on that you make a planning, and based on that you make the car drive. So for example, the example that you're showing that follow the car. So if you want to follow a particular activity, you have to follow the car. So this kind of planning should be there as well, which is not there in many simulation frameworks. And again, we also want to do assurance, so which is kind of inbuilt in Scenic and verify kind of pairs. Another project we are doing is this DARPA Tiamat. It's transfer of autonomy. So the goal would be having a robot, it will run around in a different simulation framework. And then if you learn the robotic behavior in a simulation framework, now how can you translate to another simulation or real scenarios? So that's the main goal. But to do that, you need to understand the semantics. So for example, if you want to open a door may look very different in a video game versus one simulation in the real life. And door can be of various type. One can open sidewise, one can open in the front. So, but then the the activity of door remains the same. So how to understand that and then transfer from sim to sim, or real to sim, or real to real with the efficiency. You cannot have like a lot of training data because then it becomes easier. And I think in this case, also Scenic will be useful because I think we have a session today in the afternoon where we're talking about Scenic for robotics applications, which can be either manipulation or autonomous kind of robot, which is moving around navigation. So we are interested in both. So currently we are working, we are interested in the robotics framework. For example, there's one robot for indoor, moving around, performing tasks. And now you move that robot to from your house to office building. Now, how does it work? Or move to a beach, how does it work? Because beach has this sand, which is very different from carpeted floor. Suppose you have stairs and you have a wheeled robot, you know that wheeled robot cannot climb stairs. So how do you make these plans based on your abilities and the environment? And I think Scenic will be helpful in this kind of scenarios. And again, we are also interested in these novel frameworks, novel scenarios, how to give assurance, and I think that's where Scenic will be useful. And I would like to mention one thing that we tried a different simulation environment and then tool like Cosmos or something from NVIDIA. They are not that great. And what you are doing with Scenic with very few people, I think that is really impressive because this is a very challenging task. And there are people we know that we are working with work for a year and there is hardly any like significant progress that we can think of. So I'm really looking forward to like having use Scenic in multiple of our programs. And I just give you two examples which that's currently working on. And of course, there are several other applications where Scenic can be useful. Okay, that's all. Thank you. And I'll take a question.
Hi, folks on Zoom. The other computer crashed, so hopefully, can you still hear me through this?
Yes.
Okay, we can't hear you because this one's not connected to the speaker, but while the other machine is rebooting, I think we're done with this session.
But I was thinking in this presentation, since we finished it before 10:30, he could go ahead.
Okay,
Can we do that?
okay, we're gonna do one last presentation and then we'll have the coffee break.
And it's okay that we don't have that, right?
I'll try to boot it up, but yeah. And just share your screen. Yeah, join the Zoom. It's on the website too.
Let me demonstrate how to
Oh.
defend yourself against.
Whoop, sorry.
It's on the website.
That's one. Just go to the website. Yeah, that link.
Then maybe I might need to mute this one.
Okay.
Oh, hi. Oh, sorry. Let me start again. Hi, this.
You're good, yeah. You're not muted anymore.
Yeah. So, no, I just unmuted myself, so you're right. Hi, my name is Eddie Kim. I'm a postdoc in the EECS department at Berkeley, advised by Sanjit. And I don't have, let me just briefly go over what I'm doing and then just show you a demo video just to show you what I'm doing. Right now, we interface Scenic to augmented reality setting, in particular Unity. And the purpose of it is that instead of now having to, in terms of the form factor, in terms of having to install like open capture system and so on to get humans demonstration data, actually now we're using augmented reality headset to get humans narration and demonstration information regarding how the human should interact with other agents. It could be other humans, it could be other, in this case, it could be other humanoids or robots. And from that narration and demonstration, we're trying to synthesize a Scenic program that is modeling that human's behavior. Okay. So let me show you some demo. So at the beginning,
You want to full screen it?
yeah, I'll full screen it. Okay, let me play this one. So here, imagine a soccer coach is wearing an AR headset and is teaching the system how to play. Let me demonstrate how to defend yourself against a particular tactical situation. So in this case, there are two opponents, this guy, and there's a goalpost behind me, and I'm the defender. So how do you defend? You need to carefully position yourself to achieve two things. You want to, first of all, position yourself with the ball and the goal, the player with the ball and the goal, in order to close the angle of shot, meaning you don't want to allow this player to take a shot. While the second part is defending the space behind you. So as this player takes the ball, you want to position yourself around here between the player and the goalpost. So I unpause, the situation unfolds. Now, as this player passes the ball to his teammate, you want to, again, position yourself such that you stay in between the player and the goal. Unpause again. And dynamically. Again, this player is now passing the ball back to his teammate. Again, the same logic applies. Close the angle of the shot while defending this space. This opponent is invading into your space, so you want to retract back. Just like that. Okay. So that's one example of how the narrated demonstration is. And when I say narrated demonstration, it means you're literally demonstrating physically, moving around and narrating your rationale as to why you're doing the things that you're doing. And I'm going to skip the next part. I'm giving another narrated demonstration. In fact, I'm giving variations of the narrated demonstration doing the same task. But I'll skip that for time's sake right now. And then suppose you gave like 2, 3, maybe even at max 5 different narrated demonstrations. Now from that, because Scenic is a probabilistic program, it's going to try to learn that variations that you provided stochastically. And then now, suppose it learned, and now we're going to execute that program. And then this program will now control an avatar that is going to be a proxy for the coach, right? And so that avatar would demonstrate back what it learned as a coach now. And then the coach will be the blue player.
During defense, it's important to defend the space behind you while closing the angle of shot. So don't rush out. Position yourself in between the player and the goalpost. Note that after passing, the opponent runs towards the goal. Make sure you move back to guard your space behind while closing the shot angle like this. Again, guard the space behind you while closing the shot angle.
All right. So this is a simple example of what we're working on. And kind of similar to the theme that was mentioned before, this can be also used in terms of data augmentation, as you can imagine. right? From humans' few narrated demonstrations, you can synthesize a Scenic program capturing the variations. And then using the Scenic program, now you can actually generate a lot more data with variations in terms of demonstrations. And also that demonstration also contains this explanation as well. And this explanation is also something that the system learned from the narrations and the demonstrations. So thank you. Any questions online as well?
Right. Not, thank you again, Eddie. And,